there are really three different types of classifications or types of systems to resist the effects of lateral loads. Lateral loads such as wind or seismic might be your most common ones as we're talking about building type systems. Those three typical classes or types are braced frames that you see already on this page, and then systems that don't have all these cross braces going on, and instead the beam column joints are rigid and can transfer moment. Hence these are called moment frames or moment resisting frames. And then the third broad class is where we use walls to resist the lateral effect or the shear from the lateral loads, and those are called shear wall systems. The ones you see on this page are braced frames, and there's generally, you could say, basically diagonal braced frames, a cross-braced or X-braced system, and an inverted V-brace, or oftentimes called a chevron type system. These systems are usually considered to be associated with the geometric pattern that the braces form. And so that's really one whole class where, sort of almost taken together, where the braces can resist both tension and compression, that they're stocky enough that they have significant buckling capabilities, or buckling strength that is, and so they're regarded to be, these braces are regarded to be effective in both tension and compression. Whereas a system that you don't see a lot around is just the simple tension only or tension counter cross bracing system, where when you're pushing with the lateral loads and the system wants to deform, in this case as shown with the loads, skewing or shearing to the right, that would want to cause this middle brace to buckle, because it would be in compression, this middle brace being the one going from upper left to lower right, and then the other one would be in tension. And so you see these a lot in water towers still today. You see them in really old style truss type ridges, but mostly you don't see them in buildings too much anymore. Usually it's not quite as efficient, and there's a potential jerking motion, especially in a seismic type of environment. It's not really robust enough. And then you have, well, and by the way, each of these four would be called concentrically braced frames. That would be the broad category, because the line of action of these braces passes directly through that working point that is the joint of each of those connections. Particularly here at this crown on this V, inverted V, those diagonals will cross through at the same location as the longitudinal axis on the beam, whereas if we were to push that apart like we see in this called this eccentrically braced frame, or we have, and that would have two of them versus the other one here just has one single diagonal. We do that because in this little region where you have separation, that you see the phrase a structural fuse region, that's a region of high shear, and we intentionally design that to have the ability to dissipate a lot of inelastic, or through inelastic action we can dissipate a lot of energy during an earthquake event. So there's these, that's a more exotic type of approach to things, and what you see over here on the right is one of these more concentrically braced frames. That's the V shape or the chevron type, which is a far more conventional kind of situation throughout the continental U.S., at least in terms of concentric brace frames versus eccentric. Now, all of these systems are fairly robust and strong, and you don't need to have them everywhere in the building, in all the bays in the building. And you see here one that turns out to be an eccentrically braced frame. There's a little bit of separation here. It's pretty, the longitudinal axis of the braces do come very close to intersecting each other, right along the longitudinal axis of the cross member, but not quite. You can tell by these web stiffeners that they are anticipating really high levels of shear right through that region, and they're trying to keep the web of that beam from buckling. This one is also somewhat unique in that in this parking garage, real high clearance, we actually have two of these panels, vertical panels, stacked on top of each other. Now overall, when you look at these, the first thing you should see is it looks like a truss, and that's not only does it look like a truss, but anything that does look like a truss will overall behave as a truss, with the exception of the eccentrically braced frames when you get into the inelastic region, where some things will be a little bit different as that fuse starts to help to dissipate energy. But overall, these are basically trusses that are arranged in a vertical orientation. Now the moment resisting frames have the critical factor that A, they don't have any braces, but B, the beam column joints are rigid. Now rigid in this case means that they have moment transfer, and that the resistance to the lateral loads is not through truss action like the braced frames, but rather we have moment transfer from beam to column and vice versa. And that is why we have, as you can very easily see on the horizontal pieces, the S curve for the deflected shape. You will also see that in the columns, although this particular depiction is so grossly exaggerated about the lateral displacement of the frame that it's a little bit hard to pick up on that. But every single beam and column in this particular instance will have a reverse curvature in response to these lateral loads. Now in your structural system, you might or might not have a lot of these moment frames. In steel frame systems, these are strong enough, stiff enough that you may only have them in just a few locations throughout the structural framing system. Depends a little bit on the overall level of seismic hazard. But in cast-in-place reinforced concrete construction, the integral nature of how you make such a structure is going to mean that as long as you put sufficient detailing of the steel reinforcement through the beam column joint, you're going to have moment frames everywhere throughout that particular system, such as the kind of thing that you see here, which has also got some flat slab concrete construction in there as well. And then that third system that rounds out our classification of lateral force resisting system types is the shear wall system. Here you're going to use a solid wall to resist those lateral applied forces. And so the sort of interesting thing to me about a shear wall system is that as it responds to lateral loads, not only does it resist it through shear of this very deep beam that's sort of like a big gigantic flagpole, but it's of course much bigger. But not only does it resist in shear kinds of situations, but it also actually responds a bit like a cantilever beam. The cantilever beam now just being vertical like a flagpole. You will tend to see these in tall buildings where they like to use the elevator core and the stairwell core also for shear walls. One disadvantage of shear wall systems is, of course, that you have a big solid piece on the outside of the building, and if you want to have a lot of window spaces, that doesn't work out so well. So that's why you would also tend to want to use these areas around stairwells or elevator cores for your to sort of use double usage there, to use as shear wall type systems. And yes, these holes in the walls do have a major impact on how that wall may perform, and that has to be accounted for in the design of that shear wall system.